were 24 questions, if you count the name question. And we have not graded the last question. So we haven't, because it counts the most. They're not all the same. I think somebody asked that question one night. So, for instance, there was somewhere in there, there's like 3 questions that ask you what Unicode character it is. And those are like worth almost nothing. But the ones where you actually have to do some work, or it applies some skill that you can't just look up in a calculator somewhere. And I hope nobody did that. That would be a terrible thing to get your grade or even your ability to proceed in the program questioned because you didn't follow the directions. Anybody have any questions about the exam itself? Oh, I can tell you, we have one person that missed every question except for their name. We also have one person that got every single question right, except we haven't graded 24 yet on either one of those, so I don't know what they're going to have for a grade with that. The average grade, let me look over here. Looks like it's about 60 points, or 60%. It looks like it's about 60% right now. And that's primarily because we had a couple of people that didn't attend class but came and took the test anyway, and they pulled the grade average down. Most of the people that have been here all the time, you did okay. As a class, the class did better than usual. And any questions now or anything before we move ahead? We got a lot of work to get done tonight. Mohammed?
Professor, I was just curious because for one of the questions I put like y equals to the answer. Would that be a wrong answer then? I don't know.
Not if it asks for the equation. The most likely thing people missed questions on is formatting their answer wrong or the question wrong. When they give their answer, if it's 20 milliamps, they go 0.02 amps. And that's a wrong answer because even though the number is correct, it doesn't follow the direction you were given on reporting the answers. Other people that would say specifically in the question, 2 significant digits in hex or 2 significant digits in decimals, usually the most one. And they'll give me 3 significant digits. That's a wrong answer. This is computer science. This isn't, art class where you can be creative. You need to get the answers correct. Anybody else have any questions? Robert?
So I logged in right in the middle of you saying about if you had questions about academic integrity. Is that something that you would send us an email, or would you be addressing that in class?
No, you'll get a email telling you that you need to submit such and such a piece of work. Remember, most of the people that get that, there is no question about their integrity. But I have to balance it out across. I don't want to just hand pick. So somebody says, I got one of those, and then they're the one we're suspicious of. We're going to let them prove it to us. Okay, well, the test was actually fairly easy. I've got several comments from you about how easy it was, and I appreciate that you noticed I didn't really try to bust you on this thing. I gave you questions which were all reasonable and kind of matched the state of what we needed. Okay, give me a green circle again. I want to take attendance one more time here. Or, well, one more time for now. Okay, good. Tonight we're going to start talking about a microprocessor design. And one of the advantages of learning this is once you kind of understand the basics of this design, you actually understand the design of most microprocessors in the world. They're almost all designed this way. This is just a very small one, has very few features, and is quite simple. As a matter of fact, it's called the SAP1, and that stands for Simple as Possible 1. And I know a lot of students call it the stupidest possible one, but it's the simplest possible one. And what we're going to do is we're going to look at the design. You should have in your arsenal of things if you've been paying attention in class. You should have the ability to go aha, 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 as I talk about things and see how it relates to things we've already studied. So if you go to the website, and you download /S_A_P1.gif, like GIF or GIF, and download that file. You will get the schematic diagram for the chip. Now, you might, if you have a printer close by, you might want to print it out so you can write on it. We're going to move kind of quickly through everything, and this is so you have a reference. I'm going to be writing on mine on the screen, but I'll be erasing it and writing on it and doing various things. So by having a copy yourself, you might be able to figure out some way to better take notes and not have to write all the details down, but kind of learn it as we go. So what we're going to do is we're going to go box by box on this, and we're going to understand what each box is responsible for as it sits on this bus. But to do that, we also have to understand some of the architecture of the programming language or the assembly language that would be used on this computer, because we're going to use it as inputs to the various state machines that are in the controller of this thing. So let me get a notepad here, I guess. And let's first of all, let's talk about the machine itself. It's an 8-bit architecture. Each instruction it has a 4-bit, what we call opcode or operation code, and has a 4-bit operand, which is data to be operated on. Now, not all instructions have data to be operated on. They may do some function and not need data. The machine is very, very simple, although it illustrates almost everything you'll see in a larger machine. And certainly by the time we cover about the first 3 SAPs, we will have hit all those features that you'd find in a modern processor today. For example, the ATmega 328P. Now, if you haven't bought that yet, make sure you go back to your first night notes and see what it is you have to have, because it's not going to be that many classes until we're going to need to have that in class. So make sure you've gotten a hold of that. Now, we have 5 instructions. The instructions we have are an add instruction, a subtract instruction. Let me put this one first. A load accumulator instruction, a halt instruction, so let's say an output instruction, and a halt instruction. That'll kind of put them in order by opcode. Now, the operation code for a load accumulator, the opcode is 0000. The operand is a 4-bit address of where the data is. It's not the data itself, but it's the address of the data. If you're used to programming in C or C++, it would be a pointer. If you're used to writing in Java, it would be a reference. Its purpose is to take data that's at this address, pick it up and put it into a register, which is going to be called the A register or the accumulator. The second instruction, which opcode is 0001, it also has an address. It's going to take and conceptually add wherever this thing points, the value there, to the accumulator. So the accumulator will be whatever this points at, much bigger, because we do an addition problem. Now, the steps of doing that are a little more complicated, but that's conceptually what it's going to do. The subtract instruction, same idea, except for instead of doing an addition, it does a 2's complement addition, which is a subtraction. The output instruction is 1110, And we don't care what those 4 bits are, although many times they'll be written down as 4 zeros. But we don't really care what they are. An output instruction takes whatever is in the accumulator and puts it on the LEDs that are attached to the output register. So we can basically display the value that's currently in the accumulator by executing an output instruction. The final instruction we'll have on this machine is a halt instruction. It's 4 ones. And then again, we don't care what the 4 address bits are because it doesn't use an address. And it can, normally you see 4 ones there, but it could be anything. If you had an assembler, something that could do this and write it in code, we'd probably put 4 zeros after an output by default and 4 ones after a halt by default. This is the 5 opcodes we have. Now, memory is arranged so that we have 4-bit addresses, which means how many possible bytes of memory can we have? Put your hand up if you know. We have 4-bit addresses. So how many ways can we arrange 4 bits? Dante?
That would be 8 different ways.
Well, we could do that. We have 3 bits.
Oh, sorry.
2 to the third
16
is 8. Okay, 16. So we have 16 bytes of memory. And they are bytes. They're 8-bit bytes at each address. So 4-bit addresses at each address is 8-bit byte, and there are 16 of those. We could have had fewer because we might not have installed all the memory, but 16 allows us to have a full complement of memory for the addresses we would have possible. Now, when we transfer data around, we have to be able to transfer data in 8-bit chunks if it's a piece of data, or we have to transmit it in 4-bit chunks if it's an address, or if it's an opcode. Remember that an operand in our case is either an address or it's nothing. So a 4-bit opcode could be transferred. Now we have in this thing, just as we had talked about earlier, we have something called the W bus. W bus is 8 bits wide. And when there's an address on the W bus, the address would be in the 4 rightmost bits of the bus. We have an 8-bit wide W bus. We're capable of delivering 8 bits of data around and passing it between the various boxes that are attached to the bus. But we also have sometimes instructions being passed around, and when they do, the address part we need is always in the 4 right bits, not in the 4 left bits. The opcode is always in the 4 left bits. Now, the next thing we need to do is we need to look at the picture, the diagram, and we need to try to get a sense of how everything is actually tied together. Okay, let me try to shrinky-dink this a little bit and make it a little bigger. I can almost get everything on the screen. I'm really close. Okay. In the middle, we have the W bus. The W bus has 8-bit wide wires. So there are 8 wires in the bus. Around the bus, are 9 boxes. 5 over here, 4 over here. Actually, there's only 4 over here. There's 8 boxes. This is not attached to the bus. Neither is this. Notice that some of the boxes indicate they can write to the bus. Some of the boxes indicate they can read from the bus. Some are bidirectional. Notice that they're not all 8 bits. Here's a 4 bits here. Here's a 4 bit down here. The bus, of course, is attached to each of these boxes through tri-state logic. So at any point in time, only one of the boxes will be writing to the bus. And during that same cycle or T-state, as many as necessary, but usually only one will be reading from the bus. If nobody is writing to the bus, the value on the bus would be 8 Z's or Z's because it's tri-stated, meaning it looks like nothing is attached. Now there are some additional bus material here between here, 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 and here, and actually down here. Those are not tri-stated. They're always active, meaning that they're always driven, and whoever it's pointing to is always capable of reading what's on those lines. They may not, but they, in most cases, do. So quick tour here. We have a program counter, which for most of the length of an instruction points at the next instruction to be executed. Notice that the program counter can only write to the bus, meaning that it can't change the value inside of it arbitrarily from somebody loading a bus data. Because of that, we know that the computer doesn't have any go-to instructions. Everything has got to be executed sequentially because there's no way to change the address of the next instruction to be something other than whatever it's going to set itself to be. The next register is called the memory address register, or the MAR. The MAR holds an address, a 4-bit address, so that the random access memory here has an address made available to it so it knows where to go to get the data that it's going to present when asked to present it on the bus. So the address of data or instructions is kept in the memory address register. And because it uses a back bus that's always broadcasting, the RAM always knows what the data is at that address and is always ready to put it on the bus if it's its turn to do so. This also says input on it. This set of 8 lines over here could be used to program the RAM. We're not going to talk about that, so you don't need to realize they're there, but they are. Also, you don't need to remember this is input and MAR. Just remember it's the MAR. The next thing we have is something called the instruction register. The instruction register holds 2 main, well, really 3 main, but we'll talk about 2 of them now. 2 main purposes. One of them is to hold the current instruction being executed. The second thing is to be able to rip it into 2 parts. One, which is the instruction, so it can broadcast that instruction down to the state machine that's in the controller here. And secondly, so that for instructions that have addresses, it can put the address back on the bus when it's asked to get it back in the memory address register so that we can pull the data out of the RAM. So this has a very important function as far as decoding instructions for us. And we'll talk about it in some detail about how that works. Remember, you're learning how the most advanced processor you're going to run into today works. Don't trivialize this. All these steps, although they're very small, are what is really done. So you capture this, you can go to the party and you can wave at everybody and say, I'm brilliant now. You know, and they should be impressed with you. Down the other side, we have two registers, one called the accumulator, one called the B register. They each can hold 8 bits, and the accumulator has the ability to read and write from the bus, whereas the B register can only read from the bus. Now, on a back bus, the adder subtractor is always receiving the contents of the A and B register, meaning at any point in time, it knows the answer to the question, what is A plus B? Unless subtract is asserted, in which case it knows the answer to what is A minus B. So this box is a worker B. It knows how to do addition. It knows how to do subtraction. It also can put the answer on the bus when asked to. Finally, we have something called the output register, which is hooked to 8 LEDs. And basically, it's just a register. It can hold any arbitrary 8 bits we want, usually our answer, so that we can light up the LEDs to see what the answer is. Because a computer that can't tell you what its answer is isn't very useful. If it can't have some sort of input, it's not a very useful computer. Robert?
So, question on the adder subtractor, and it only really matters when it's the subtractor. You are subtracting the B register from the accumulator?
That's correct.
Okay.
It's always B from A. Okay, now let's verify that all the boxes have the correct signals for what they can do to the bus. Program counter can write to the bus. So what does it need? Does it need an enable? Does it need a clock? Does it need a load? Which of those three does it need? Raise your hand if you know. We spent a whole evening talking about this. Patricia, what do you think?
If it wants to write, it needs an enable.
Right, and it's got one. EP is enable the program counter. Okay, this guy can read the right 4 bits from the bus. What signals does he need? Scott?
Needs a load
And
a clock.
And he needs an edge-triggered clock. He's got an edge-triggered clock. He's got a load. So he meets the requirements to be able to do that. Notice this guy also has the ability to have a clock, but he doesn't have a load. So this clock must be used for something else. What can the RAM do? The RAM can write to the bus. So it needs what type of signal, Robert?
It also needs an enable.
Right, and it's got one over here which is traditionally named after the pin on a memory chip, which is called chip enable. Notice that some of these are high-going signals and some of these are low-going signals. When we talk about them in general, I'm going to just talk about them without remembering which ones are high and which ones are low. But on an exam or having to build the thing, you'd have to know which is which. But I'll just refer to this as chip enable, and we'll just remember that it is a low-going signal. Just like up here, I'll remember the clock is low-going and the clear is low-going. But when I talk about it, I'll just talk about clock and clear, except for one special thing about clock up here we'll talk about later. There's no signals required for this. Just the output of the memory address register is attached to the address lines of RAM all the time. The instruction register has to read and write. Notice it can read 8 bits. It can only write the rightmost 4 bits. What signals does it need in order to read? Patricia?
A load and a clock.
And there's a load and an edge-triggered clock. What does it need in order to write to the bus? Mikhail?
It needs enable.
Right. And EI would be enable the instruction register. Accumulator can go both ways. What signals does it need? How about for writing to the bus? Samir?
Would it be to load the edge trigger clock?
We want to write to the bus.
Is it an enabler?
Right. We have to enable the accumulator. And of course, the read will be the other two he said. We have to have load accumulator and an edge triggered clock. All the clocks are actually tied together except for this guy. Here's the adder subtractor. We have two signals. We have EU, which is enable, meaning this guy can write. He can write. He can't read from the bus because he doesn't have a load in the clock. But he also has this extra signal out here called subtract, which is asserted anytime we need to do a subtract. And we have an instruction that does a subtract, so we'd have to be able to do that. Notice it also is always seeing whatever's in A and whatever's in B, and as a matter of fact, is always solving the problem. So because it can see the answer, even if we don't need the answer yet, it is producing a sum. If subtract is asserted, it's producing the difference. So that's always happening because this is a back bus and doesn't require any tri-stating. Output register can only read from the bus, so it needs what signals? Mohammed?
Will be load in the clock edge triggered.
Right, it needs a load and it needs an edge triggered clock. This guy, of course, needs no signals because whatever is inside of him is always being broadcast into the binary display, meaning this guy is always displaying whatever's inside the output register. Now notice down here below, the instruction register has a back bus with 4 bits. The 4 bits here are the current instruction. I'll just put INST here. So once we get the current instruction into the instruction register, it can broadcast what instruction we're doing into the controller sequencer. The 4 bits here are the address portion of an instruction. Some of the instructions had, remember the 4 A's at the right-hand side? Well, we have to strip that address off at some point, get it in the memory address register so we can go to the RAM and get the data we need. Finally, down the side here, we can see that the controller sequencer is responsible for generating the clock, the not clock, the clear, and the not clear. And additionally, it can generate 12 control signals. The 12 control signals it's going to put out are CP, EP, LM, CE, LI, EI, LA, EA, SU, EU, LB, LO. Any of the control signals that we had to control whether we're reading or writing from the bus. Notice it produces clocks and clears over here. Clock and clear kind of here. They're the inverted ones, and here are the non-inverted ones. Over here we have this clock. Here we have a clock. Here we have a clock. Those are all the clocks that are being generated here as well. So the controller sequencer is pretty much telling everything what to do and keeping things synchronized. Now, when we look at the implementation of the program counter, one of the things we're going to find out is that internally, it uses JK flip-flops. So let me grab this, if I have it over here still. Let's assume for a second the clock signal looks like that. Always starts low and then goes high. Half a period there, half a period there. So the period is this long. So if this is clock, what would not clock look like? Robert?
It would just be the inverse. So you draw straight and then go down and then over and up and etc.
Okay, it's exactly synchronized. Now, when we have a clock cycle, we've talked about this before. At the start of clock, we're going to assert any control signals. So the controller signal generator will generate some of these 12 signals. It'll hold it to the end of the period. Halfway through, we get the rising clock. That's when data actually gets transferred into a box. Now, if that were the case, and we had the program counter and we're doing it on the falling edge, remember what I just said. This is going to have flip-flops in it. And the type of flip-flop is going to be a JK flip-flop. What did we learn about JK flip-flops in terms of the clock? Scott?
On the rising edge, it will kind of like take in data, but it won't write it out until the falling edge of the clock.
Right. So we're in the program counter, we're using the falling edge because we know it's at exactly the same time as the rising edge of the real clock, which will cause any JK flip-flops in here to move their data in synchronous shape with everybody else. So this can't be clock because we'd be off by half a period. So we synchronize it by using not clock, what's this guy, not clock, for the JK flip-flops. Okay, now, internally, the machine is going to take each of these clock cycles we have, and it's going to generate a series of them. There are actually on this machine 6 T states. T1, T2, T3, T4, T5, and T6. Each of these T states is 1 period long. And for all of the instructions, we allow there to be 6 T states, even though we may not need that. We're not going to optimize this machine by getting rid of extra T states. We'll just do nothing by asserting no control signals during those T states. Now the machine has a ring counter, which is going to have a 1 in one of 6 positions to tell us which is the current T state. So you can think of this entire 6 T states, which means the clock goes low, high, low, high, low, high 6 times. You can think of it as having 2 parts to it. The entire thing we're going to say is the instruction cycle. The first half of it, the first 3 T states, is going to be called the fetch cycle. The last 3 T states are going to be called the execution cycle. Each of these T states could be given a name, but we'll just think of them as having a particular function. In the first T state, we don't know what instruction we're getting ready to execute. So one of the things we'll have to do in that T state is we'll have to put the address somewhere where we can use it. So the first T state is called the address state. The second T state is called the count state. Well, all we're going to do during that T state is we're going to make the program counter be 1 bigger than it was. So it points to the next instruction. Remember, our instructions are sequential through memory. If we ever get to 15, we'll roll over to 0 again. So all we need to do is bump the count in the program counter during T2. And all instructions need to do that. In the next T state, we're going to actually recognize what instruction we're executing. And of course, all instructions need to do that so they know what to do during the execution cycle. The one exception to using all 6 t-states is the moment the halt instruction recognizes that it is a halt instruction, it blocks the clock so we can't see any more t-states. So it literally halts the clock. So really the halt instruction is going to stop halfway through T3 because that's when it's going to recognize the current instruction as being a halt. All the others will have all 6 t-states, although they may not use them all. And as we do think about each instruction, we'll flesh out what T4, T5, and T6 do. Okay. First of all, let's look at the load instruction. If we say load the accumulator from address, let's say address 8, that's going to degenerate into the operation code of 0, 0, 0, 0, 1, 0, 0, 0. Now, assuming that in T3 we had just recognized we have a load accumulator instruction, what T4 has to do is it has to get the address of the data into the memory address register. So I'm just going to say the address. Let's call it D address, data address. Put it into the memory address register. This is T4. In T5, it's got to take whatever data is now present in the RAM. Remember, that's the address, so the data wants to come out of the RAM now. So the RAM data has got to be moved to the accumulator. That's T5. Since that's all the load accumulator needs to do, in T6, the load accumulator will do nothing. And we'll walk, don't worry, we'll walk through each of these in quite a bit of detail. Now the add instruction will be a little bit similar to that. I'll use the same address because we're just using it as a reference. Remember, I'm writing in binary here. So the opcode is 0001. And then 1000 for the address, which is really byte number 8. Be the 9th byte of memory because we have a 0 byte. We have to do the same thing we did here. We have to do data address, which is in the instruction, has to be moved to the memory address register in T4. The next thing we have to do is we have to take what's in RAM, and we have to move it to the B register. That's T5. We're adding what's in B to A. So we're taking whatever this address points to, taking the data there and adding it to what's currently in the accumulator. Now, the next thing we have to do is we have to take what's in the adder subtractor unit, I'll just call it the unit, and put it into the accumulator. And that's going to happen in T6. the subtract instruction. There's 1,000 again. So that would be the address and the data, or the opcode and the address. This guy is going to, very similar to the add, take the data address, put it into the memory address register in T4. Take whatever's being pointed to in the RAM, move it into the B register in T5. Then take what's in the unit, move it to the accumulator in T6. Now that looks a lot like add, doesn't it? There is one difference. In T6, we also insert the subtract signal. So when we move it from RAM to the B register, the adder subtractor unit will have the sum of whatever's in B and the accumulator. When we get ready to take it out of the accumulator and move it to the, when we take it out of the unit and move it to the accumulator, since we asserted subtract, it will have already done a 2's complement on the B register, and this will give us a subtraction answer put into the accumulator. So there's the 3 power instructions on this machine. Let's look at the output instruction. Oops, that's the output. Could have anything there, very often zeros. So it's 1, 1, 1, 0, 4 zeros. Move the data address into the memory address register. Well, actually, no. In this case, what happens is, remember, all we have to do is get what's in the accumulator into the output register. So we can simply take the accumulator's data and move it straight into the output register. We can do that in T4. And we don't need T5 or T6. The halt instruction never makes it to T4. We stopped him halfway through T3 because we recognized we were executing a halt instruction. Okay, any questions about this so far? Robert?
So you mentioned during, excuse me, during the subtraction that it would already have it in 2's complement. Is that done during one of these steps?
When we assert SU, it causes the B register to have the 2's complement in it.
Okay.
Okay. Let's look at a little piece of program code, and then let's go over to the machine and walk it through. I'd like to keep some of this on the screen for you. Okay, at address 0 in our machine, we have that. Address 1, we have at address 2, we have address 3. Oops. I think I'm losing it here. A little further down here, let's see what we have. I'm going to write some addresses here. Okay, so we said, here's our opcodes. What are the 4 instructions we're getting ready to execute? I'll give you a clue. First instruction, the load accumulator from address 0111. What's the second instruction? Daniel? Or, I mean, Dante? Your name looks like Daniel from where I'm sitting twice now tonight.
The second instruction would be add.
Okay. And what are we going to add?
We're going to add 0110.
Well, that's the address of the data. That's not the data we're adding. That's the address of the data. Okay. What's the next instruction going to do? Or its opcode? Hermel?
Would it be subtracting the data at address 0000?
Well, what's that opcode? 1110.
Oh, output actually.
Okay. So we have an output instruction, and we don't care what the data is because we don't use it. And what's the last instruction there? Patricia?
Isn't that a halt?
Yeah, that's a halt. And again, we don't care about the address portion. It could be anything. So the first one says, go to address 0111. Well, here's 0111. What's there? Well, let's assume we have there that number. What number is that in decimal? Robert?
That's 9.
Right. So the instruction is going to basically add 9 plus something else. Okay, so but at 111, we're going to load the accumulator with a 9. Now we're going to add to it whatever's located at 0110. What 0110? We have the number 1. So what is this instruction going to do? Scott?
It's going to add the value at address 0110. In other words, that 1 to the 0 to the 1001 that's already in the accumulator.
Right. And so it'll add whatever it picks up from the memory address to whatever's in the accumulator. In this case, there's a 9 in the accumulator, and there's a 1 because we can see the data. But we can't see the answer yet, so we need an output instruction, which will take whatever's in the accumulator and move it to the output register, which in turn drives the LEDs. Then we'll have a halt. Program's over. So when program ends, we'll see the number 10 looking at us out of the LEDs. So let's walk through all of that happening. When we first start the program, we have to clear the machine. There's a button we push called clear. There are 4 things which are cleared when you do that. You want to remember these. One of them is the program counter gets set to all zeros. It's only 4 bits wide because there's only 16 bits of memory in the computer. Now, while we're talking about that, the data and the instructions are commingled in this memory. In computer science terms, that means this is a Princeton architecture machine, or something called a von Neumann machine, as opposed to a Harvard architecture machine, which our ATmega 328P will be. So this one has in the same set of memory the data it's going to operate on and the instructions. If the program counter ever points at it, it treats it like an instruction. If it doesn't or uses it from an address, it's treated as data. But it's all mixed in together. There's not separate memory for the program and separate memory for the data. So this is called a Princeton architecture or a von Neumann architecture, the same thing. machine. So there's 4 zeros in here. The other place that when clear is pushed is we have to have the instruction register make sure it's pushing out the 4, out this arrow down here, 4 zeros. So it has to set the current instruction to being 4 zeros. Otherwise, when you see what causes the machine to halt, the machine could never be started again. So we basically have to set it to something that's not all ones, and the thing it sets it to is all zeros. The 2 other things that have to happen when you push clear are the main system clock has to be set low. So we start at the low part of a clock. And the last thing, although we haven't talked about it, well, we kind of did, is there's 6 T states. We have to be put into T1. So we're always starting the first instruction in T1 of the first instruction. Those 4 things: clear the program counter, clear the instruction that's currently stored in the instruction set register, set the system clock low, set the T state counter, the ring counter to T state 1, T1. So assuming we're in that state, then we have to look at what is the first thing that has to happen in every instruction. Well, in every instruction we're going to execute, did I write those down on this piece of paper or were they on the other one? Oh, I wrote them underneath here. We have to get the address of the current instruction somewhere useful. The current instruction's address is right here. It's these zeros, which we just cleared it to say. It basically, when you clear it, you're telling the program counter, start at the beginning. So those 4 zeros, in order for us to get the instruction out of memory, have to go to the MAR. To do that, the program counter has to write to the bus, and it's only going to be writing in the 4 rightmost bus positions. And the memory address register has to be set up to load on the rising clock that data from the bus into its registers. At which point, of course, they'll be broadcast and the RAM will know what the first instruction is. So if we say enable here, enable the program counter, EP, then we're going to put the data on the bus. The data is only in the rightmost positions. So what we'll see on the bus will be ZZZZ, because nobody's writing to those 4 positions, and the other 4 will be 4 zeros. Halfway through the T state, the clock will go from low to high. Because this is on the bus and because this is looking at those 4 signals, this guy will now have those 4 zeros stored in him. We're still in T1, but because that's getting broadcast out the 4 here, the RAM will immediately know that it needs to make ready to put on the bus when it's asked a load instruction, which is addressing, we used address 0111 over here. Now it's all set to put it on the bus, but it can't write it on the bus yet because the program counter owns the bus. It's writing to it. So during T1, we had 2 signals asserted. Enable the program counter, load the memory address register. Now, like I say, I'm not going to put the sex on these. You really made a 0 here, but I'm just going to use the names over here. So during T1, we enable the program counter to load the memory address register. At the end of T1, we enter T2. During T2, the only thing that has to happen is the program counter is going to bump up by 1. That means the bus doesn't have anything on it useful, and the bus changes from what was there to all Z's. So there's 8 Z's. Nobody's reading it anyway, so it doesn't matter. But the program counter has count asserted. So during T2, I lost where that went there. CP is asserted. Halfway through CP, the clock goes low, or not clock goes low, so we're latching to not clock halfway through. And that means that this guy now contains 0001 at the end of T2, because that's where the next instruction is. Now we enter T3. During T3, we've got to get the data that's in the RAM, which is our instruction, on the bus and load it into the instruction register. To do that, we need to do a chip enable and we need a load instruction register. So start at T3, this data will appear on the bus. So it'll be 4 zeros, 0111. It'll be loaded into this. So now the instruction register has the 4 zeros, which are the opcode, and it has, you can think of it separated, it also has the address. The reason we separate it is because it's going to take these guys at this point forward and broadcast them through there. Turns out to be the same value this was, but nevertheless, we're now broadcasting 4 zeros to the controller sequencer. So it knows what instruction we're executing halfway through T3 when the clock goes high. Not until then do we know what instruction we're executing. Now it's saving the address because the instruction may use the address. Ours does. Remember for a, I don't know where I put those. They're probably up here. For a load during T4, I need to take the data that's in the instruction register, that happens to be the address part, and put it into the memory address register. So since we know this is a load accumulator instruction, during T4, we need to enable the instruction register so it can write to the bus. And we need to load the memory address register so that address gets moved into the memory address register. So during T4 for a load accumulator instruction, this 0111 goes out on these 4 bits here, meaning that the bus will contain 4 Z's, and in the case of this program, 0111. Halfway through the T state, the clock ticks, and this 0111 goes into the memory address register. And since it's being broadcast down to the RAM immediately can go to that address, 0111, and it can see that it has the number 9 there, and it can get that number ready to go. Now for a load accumulator, we only have one other thing to do. we need to take what's in RAM and put it in the accumulator. So the RAM has a 9. So at the start of T5 for a load accumulator, that came off the bus. And this is enabled, so we'll see the number 9 on the bus. Halfway through the clock will tick. It'll be loaded into the accumulator. And we know that the adder subtractor is adding that number 9 to whatever is randomly in B. So we don't know what's in here, but we know an addition problem that maybe difference just happened. T5 in, well, what signals do we assert during T5 for this? During T5, we had to chip enable to get it onto the bus and do a load accumulator to get it into that. And during T6, oh, I got it there. T6, we're going to do nothing, assert nothing. So during T6, nobody's writing to the bus, so we'd expect to find 8 Z's on the bus. T6 ends. Now we're in the first T1, which means we're going to use this to determine what to do next, because this is where the next instruction is. Now, did that flow reasonably make sense to you? Give me a green circle if it did. Give me a red circle if you're really confused right now. And it's okay to be red. Now, it's critical to understand what's on the bus in every T state. By looking at this, we can always tell whoever's enabled. So whatever's in the program counter will be on the bus. Nobody's enabled, so there'll be all Z's on the bus. The data that's at the address of the first instruction, which means the first instruction is on the bus during T3. During this, we're going to write the address portion of the instruction back on the bus so that we can go to the get the data here where we enable and pull that data out. The load is always the place we're targeting the thing on the bus to go to. Of course, we didn't need to do something. So I would jot down somewhere that these are the signals you need in order to do a load accumulator instruction. Now remember also, some of these like EP or EI only write 4 bits to the bus, in which case the first 4 wires have Z's on them and the last 4 contain the data. Okay, without going step by step, let's work through what the T states must be for an add instruction. During T1, we have to take what's in the program counter, the data in here, and get it into here. So we can anticipate what that is. Enable the program counter, load the memory address register. During T2, we need to bump the program counter up by 1. So the only signal we need to assert is CP. During T3, we have to get the data we are addressing, which is the first instruction. We got the address, we put it here, so the first instruction's here. We have to put that on the bus and get it into the instruction register. So to do that, we have to chip enable, and we have to load the instruction register. Notice that the 3 T states for the fetch cycle for both of these instructions are the same. And I'll give you a clue. They're the same for all of the 5 instructions. It's only now things get interesting. Add is slightly like load in T4. It's going to do the same T states, but it's after that it will diverge. So T4, we're going to have to enable the instruction register so that we can load the memory address register with the address out of the instruction. Now in T5, we have to go to the ROM or RAM, pick up the data and get it into the accumulator. No, I'm sorry, into the B register. So to do that, we have to chip enable to get it on the bus. We have to load the B register. Now at that point, because we have, let me use lowercase. I'm being inconsistent there, but it's whatever types on the keyboard. The moment since I already know what's in A, the moment I put something in B, I know what the added addition problem is here because I can work it by hand. So if somebody asks you, during T5, what's the value inside the adder subtractor, and you had this program, you could say, well, it's a 10 because we're adding in the number 10. But here's the problem with that. That number wasn't transferred to the rising clock. So if they say during T5, that's not the answer that's in there until the rising clock. It won't be there until you latch it in off of the bus and change the B register. Remember, B didn't change while the low clock, it changed as it went from low to high. And in the end, we have one more task to do down here at the end. In T6, we have to enable the unit with the adder subtractor, and we have to load the answer into the accumulator. Now, had we been doing a subtract instruction, during T6, we would also assert the SU signal. In this case, we'll show it as an add because that's what our program does. So right now, if we were to go through and look at the registers, we bumped it once here, we bumped it once here. So this would right now contain the number 2. What we'd have here would be the address from the add instruction, which is a 0113. We'd have that value, which is the 10. I'm sorry, the 9. I kept saying 10, but that's the answer. It's a 9. And down here, we know the last instruction that we saved was an add, so the 4 bits being broadcast to the controller sequencer are 0001. This, of course, is 0111 still, because we had to take it, put it here. So that's where we are on this side of things. This contains a 9, this contains a 1, this contains a 10 at this point. So we could look at all those, and we enter T1 now for the next instruction. The next instruction happens to be an output instruction. Our first 3 T states are the same. For the out, during T1, we're going to enable the program, load the memory address register. During T2, we'll do a CP. During T3, we'll chip enable and we'll load the instruction register. Now we only have one thing left to do, and we'll do that in T4. In T4, we have to enable the accumulator and load the output register. T5 and T6, we do nothing. T5, nothing. In T6, nothing. I don't think I'm typing T6, but maybe I did. The only instruction we haven't done is the halt. And let's think about it. We'll enable the programmer and load it in the memory address register so that the address of the halt instruction, which in this case is a 3, would be put into the memory address register. It would notice that there's this instruction there, make it ready to write. We'd bump this up to the next address, which is a 4. We're never going to get there, but nevertheless, we still bump up the program counter. Chips enabled, we put the halt on the bus and then into the instruction register. We don't have any data portion, so we don't need a T4, 5, and 6 at all, because halfway through T3, when it recognized, because we were broadcasting down into the controller sequencer, 4 1s, when this guy sees 4 1s immediately, which is halfway through T3, it asserts the halt signal. The halt signal is attached to the inputs to the clock, so it'll stop the clock. And basically our program can't do anymore. It won't even finish T3. But effectively our program will be stopped and everything will just be stationary until we push the clear button. We push clear, it'll start over at 0 and do the same thing. Anybody have any questions? Okay, some fairly simple things to think about. When the start button is released, meaning the program begins, what T state are we in? Raise your hand if you know. Got to be more than 2 of you. Got to be more than 3 of you. Scott, what do you think?
T1.
Okay. And the reason is because that's one of the 4 things that gets cleared when we reset the processor, we issue a clear. What is on the bus once we've released the clear? We're in T1, low clock. What's on the bus? Andrew?
Is it all Z's?
Well, you have to think about what signals are asserted at the start of T1. Dante?
I was gonna assume it was gonna be all Z's, but I'm gonna take a guess that it might be. Is it zeros?
Well, it's halfway between. Notice during T1, we always have EP and LM asserted, which means the program counter is writing on the 4 right lines. And since it's set to a 0 on clear, that means that we have 4 Z's followed by 4 zeros on the bus, always when the program begins. What's on the bus during T2? And that's any T2. Mikhail?
All Z's.
That's right. Nothing is being written, so it's completely loaded up with Z's. Let's look a little bit at the internal architecture of the machine. And I'll give you a file to download so you can follow along with me. It's sap1.zip. You just go to the website. And yeah. So at the end of the website, slash sap1.zip. Put it there and put it perhaps here. I apparently couldn't copy it there. But sap1.zip, when you get that, we're going to look at the pictures and things on my screen, but you may want to have that just as a handy reference. So let me clean some of this up before we do that. I can always reload that. Okay. We're going to talk, first of all, about this guy. We've seen it before. And we're not seeing a full picture of it here, but this is basically the program counter. I always make them just big enough for the SAP1. We have 4 bits that are used for the address. And as I mentioned to you earlier, we're going to use JK flip-flops, which means we need to use the inverted clock. Notice that we have a signal called count attached to the J and K. If count is high, this causes each of these to toggle in turn, which means this guy is toggling twice as fast as this guy, who's twice as fast as this guy, who's twice as fast as this guy. So we'll count in binary from 4 zeros up to 4 ones, and then we'll overflow into 4 zeros again. We know that there is a tri-state buffer, though it's not shown in the picture, just beyond these queues, and it's controlled by the EP signal, the enabled program counter signal. Now, we could actually use count to halt the counter, because if we ever drop J and K down to low, then we would cause it not to count any further. However, we also need this in normal practice, because think about how often do we bump the counter? Do you remember? See if you remember that. How often per instruction are we going to bump the program counter? Miguel?
Once.
Well, that's once per 6 clocks.
Yeah.
Where we have 6 T-states per instruction, and each instruction only has in it 1 time where we're going to bump the thing. So the count value that's here is actually the signal we call CP. So only when CP is high will the clock make a difference. We also know that these are tied to the buffer, and the control of that buffer, the thing that enables the tri-state buffers, is going to be the thing that allows us to present the data, enable the program counter. We don't have that shown in this picture, but you can envision a tri-state buffer hooked to this, which is then hooked to the bus, and EP is the controlling thing of that. Remember, the buffer looks like this. It has a third leg. Well, that third leg is the EP. And when it turns it on, this works like a buffer. The data just passes through. When it turns it off, this becomes high Z, and the bus floats. So that's our program counter. Nice friendly box. Some of the boxes look like this. This we've seen before. This is the kind of the equivalence of what we would do if we have a thing like the memory address register, where at a given time we have to load 4 things from the bus. Well, on the memory address register, this would be the load memory address register signal. On the load instruction register, this would be the LI signal. On load accumulator, this would be the load accumulator, or the load B in the B register. This could be the same thing for the load the output register. Sometimes it'll have 8 bits instead of 4, and they're synchronized loading with the clock. Usually the clear is not made operational. Remember, on this, none of these are ever used with the clear signal. The program counter is cleared. The instruction register, the program address portion is cleared, not the entire thing. So these loads legitimately use a register that's either 4 of these or 8 of these in size, and can either recycle the current data or load new data, depending on how its load signal is associated. And it's tied to the rising clock. So if signal is asserted here, it'll be steady by the time we get to the rising edge. This guy is actually just another picture. Oops. Of the program counter without some of the fancy clearing and all that stuff on it. I don't know why I had both copies in here. I probably put this one in and then found the other one. But again, this again is another view of the SAP1 program counter, just a different take on it. Now the unit, the adder subtractor, we've seen this before as well. Again, we would extend it to 8 bits. But remember, we had the ability to pick whether we're letting B come in or B's complement, depending on how we set the subtract signal. Plus, it inverted the bits and potentially inverted and added 1, which is exactly how you do it to its complement. So the A register always just comes in clean. If you're doing an addition problem, subtract is not asserted. This, of course, is our SU signal in the SAP1. The outputs here, of course, are all tri-stated. We just don't show them in this picture. And we have 8 of these instead of 4. This data is constantly coming from the accumulator. It's not like you have to wait for it. Whatever's in the accumulator, that's what's there. Now, it may be that this doesn't change until halfway through the cycle, which is the way the accumulator gets loaded, or the B register gets loaded. So the addition problem it's working might change at that point. We just have to be aware of what's in the registers, knowing that this is always producing an answer. It's blocked from the bus by the tri-state buffers until we say to assert it. And when we say assert it, it'll always go out on the low clock. And a little peculiar thing can happen on the rising clock, and I'll show you that later. Anybody have any questions about this guy? We talked about this being a fairly useful circuit when we talked about it under digital component and arithmetic. Okay. Let's take a look at the controller sequencer. Did I get him to fit? That's pretty close. Okay. The controller sequencer is basically a state machine. Remember, a state machine changes state based on its current state and whatever the inputs are at the current time. Outputs are always synchronized to a clock, which is exactly what we need. So the primary things we have in here, if we were to break this into its main components, are over here on this side, we have the instruction decoder. Up at the top, we have a ring counter, which is going to count for us what T state we're currently in. then finally, down here at the bottom, we actually have the state machine's combinational logic that down at the very bottom produced the 12 control signals. So let's talk our way through this. Let me see if I probably can't get this any better fitting on the screen here. So I'll have to talk kind of off the left-hand edge. Remember, the instruction register is pumping 4 bits of data, which are the left bits of the instruction, 7, 6, 5, and 4, into the control matrix all the time, but the instruction that is going to be correct for a particular thing is correct starting in T3. In T3, we load the current instruction, never to be changed until we re-enter, T1 again. It's actually T3 again. But because of that, after T3 begins, well, not after it begins, halfway through T3, when the clock goes high, this will be producing the correct instruction. So this guy can decode which instruction we're currently working on. Notice it used our bus structure here. Here's A, B, C, and D, that's our 4 signals. And then here are our 4 inverses of those signals. So we can simply take this AND gate and connect it to what we want to decode. If we connect to 0, 0, 0, 0, we're decoding a load accumulator instruction. 0, 0, 0, 1 must be an add. 0, 0, 1, 0 is a subtract. 1, 1, 1, 0 is an output. And if we ever decode a 1, 1, 1, 1, which we would decode it halfway through T3, we assert a halt signal, which stops the clock. So we never see T4. But because we can decode this, the moment we get above T3 in T4, T5, and T6, which if you notice that's the only place the instructions set were different, we can use this to tell us what set of things we should be doing. Now, at the top, we have a ring counter. Notice that the only one flipped over is this guy. K and J are inverted and not Q and Q are the opposite of the others. So when we do a clear, this guy goes to a 1, all these go to zeros. Meaning this guy represents T1. This guy is T2. T3. T4. T5. And T6. Now what we want to do is we want to follow the signal line from the top part of the flip-flop. So from not Q, or from Q, or from Q, 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 and Q. Follow that down to this first set of lines. What that tells us is the bottom line down here is T1. The second line is T2. Third one, T3. T4, T5, and T6. Now, this may sound like a lot of detail, but remember, we're talking about all CPUs going forward. So what we're talking about here is true on the Pentium you're running. Or you probably don't have a Pentium, you probably got something a little slicker than that, but the processor you're using in your machine uses this same underlying architecture. It may be tweaked a little bit or optimized a little bit, but if you can fundamentally understand this, You can take the data sheets for any particular microcontroller or processor and figure it out. You want to be able to do that if you want to be a computer science genius. And I want all of you to be that. You know, I want to say genii, so I can pluralize it with an I on the end of it instead of geniuses. Okay, so we have a line going across which is tied to something else in the matrix. So if I look from below, I see some things reaching up and connecting to those lines. Notice that the T1 line right here, if we go across that line, we'll find we have two things connected. Now, if we follow those down, one of them is EP. The other one goes through this OR here to this load memory address register. Now, we would expect other things to also turn on load memory address register. We saw that in the signals. There's other instructions. But we're clearly tied to enable program counter, load memory address register. Those are the two signals we need to assert during T1. Let's predict. T2, what signal should we find? Anybody raise your hand? In T2, what signal should we be hooked to? Matthew?
CP.
Okay, let's double check that. Here's a line that's hooked to T2. And we follow across, the only other thing is the thing that goes up to T2. So if we follow this straight down, look at that, it's hooked to CP. So the only signal that would be turned on is CP. There's T2. So if we didn't have that other chart, we could figure it out from this. Let's look at T3. What are we expecting in T3? Patricia?
The chip enable and the load and instruction.
Okay, so we would expect chip enable to be used different places, but load the instruction register only happens here. So let's see if that's true. Find the line that has T3 on it, which is the third one up. Here's one of the signals here. Here's, well, this is going up to T3, so here's one here. And do we have another one anywhere? Well, let's see. What is this signal going through to? Chip enable, and is going to get the other one from some other state. And load instruction register. So it's doing what we expect it to do. Now comes the tricky part. T4. Let's assume that we're doing an output instruction. Well, what we're going to have to do is we're going to have to make use of our control matrix a little more thoroughly here. Not only do we have to be attached to T4, meaning it has to attach to that line, we also have to be attached to this output line in terms of which gates are potentially part of the output stuff. And if we look at output, output follows along to here, this gate right here, and this gate right here. Now, it is ANDed with something else. So let's go up. T4, T4. So there's our two signals. One of them is enable accumulator. The other is load output register. Exactly what we expected to find in T4 of an output, an output instruction. Why don't you try to do T4 for an add instruction? See if you can figure out from the chart. I mean, we can look up the thing, but the point is use the chart to figure out what it is. Because almost guarantee at some point you're going to get one of these charts, And it's going to say, we added a new instructions. Tell me what the signals are it uses and how it works. Okay, what's the first thing I should do? Robert, what do you think?
I would look along the add line and see where add connects with any gates.
Okay, that'd be one place we could start.
And also the same with the T4 line where it connects
Okay,
to the
so
same gates.
here's one of our guys right here. So potentially, I'm just going to put an A in this guy. Potentially this guy is on. Add here, potentially this guy. Looks like add is on here again. Here's add over here again. Adds here. Can't read that. And add is here. Double check me that I'm putting them in the right boxes. Now, we're concerned about T4. So we would look along the T4 line to determine which ones of these are possibly affected. Well, T4 is right here. So this guy, we follow him down. He is connected to this. So this is a likely signal right here. We'll follow that through and we'll see load memory address register. So I'll put a little square around him for now. This guy is also asserted. Follow him down. And he just all by himself goes to load instruction register. That doesn't sound right. Oh, I'm on the wrong line. I want the fours. Here he is over here. So this guy is tied through to this guy. So this is potentially a good enable instruction register. Now we know we found the two instructions. Let's see what happens on the ones that don't work. Here's one. When we follow it down, we're not connected to anything that I put an A in. We're not connected to this guy, for example. So we know he's not asserted during T4 for that signal. What is would be this guy if you have an output instruction. Or in the case of, where was the other T4? This guy, if you have a subtract and add, we've already got this guy underway. But it's a different T state when we do that. So we can figure out what particular signals have to be asserted by just tracing our way through the control matrix and literally see what the computer would be doing. The 12 signals down at the bottom down there, in conjunction with this T-state counter and the clock, go tick, 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 and the machine keeps moving. That's what causes the computer to actually solve problems. It's just a big state machine. This is the combinational logic. These are the inputs. You can think of these as inputs or combinational logic, but usually as inputs because they're different. This stays the same. These change in terms of how we're hooking them into the circuit, but I would kind of think of them either way that works for you. And then finally, we have the clock itself that's ticking. So again, just as a reminder or review, what are the four things that get set when we clear the processor in order to start it running? Ramel?
The program counter T1, declaring the instruction and like setting the clock to low.
Okay, that's right. And the reasons you can see why are 0, 0 in the program counter. We need the to be pointing at the first instruction. The clock needs to be low because if it weren't, we wouldn't have time for the signals to take place before we saw the next rising clock. And worse, we might actually start on the edge of the rising clock and just completely miss a clock. And the T counter could get out of sync with us. T counter needs to be in T1 because we always want to start with that first, put the instructions address on the bus and put that in the memory address register. And finally, the only way to stop halt from being decoded is if once it halts, there's going to be ones here. And it'll stay halt forever unless we change those to something else. So clear changes those to 0, which means halt releases this signal and we're no longer halted and the program can begin. And that's the rationale behind why those are the way they are. If somebody showed you a picture of the machine and they said, what's in the, let's actually do that. Let's, should have one in here. Is that our machine? Whoa. Am I going to be able to get that so we can see it? Probably not. But we're getting ready. Let's do this kind of like a little quiz. I'm not going to collect it or anything, but quiz yourself on it. See how good you are at answering the questions. We've been running the computer for a while and we just reprogrammed it. Remember, we can reprogram it through this with circuitry I'm not going to show you. We just pushed clear and we're ready to release it to run the machine. First question is, what value is inside the program counter? That's question 1. Second question is, what is inside the memory address register? Third question, what is the byte of data that's being pointed at in RAM? What value does it have? Because it would be the first instruction. Because at least that'll be the first thing we ask it to present. What's inside the instruction register at this point? Then you're down the other side. What's in the accumulator? What's in the adder subtractor? What's in the B register? What's in the output register? And then finally, what are the values now of the 12 control signals in terms of their logical value, not their 0, 1-ness? Just which ones are asserted, which ones are not asserted. So just try to do those. Think about it. Some of this you should be able to just kind of deduce in your head. You wouldn't have to look at your notes as you start to understand how this machine works. When you think you have reasonable answers for those, give me a green circle. I'm not going to wait till everybody's done, but I want a few people to be done. You can kind of think of the state machine, the Moore state machine that's built into this, actually having it as its flip-flops, those 6 T states. That's the name of each state, because it's a one hot, you're in T1, you're in T2, you're in T3. And it contributes partially into the combinational logic, but so did, and if you think about the ones we did, the current state is always fed back so that we can use the combinational logic with the inputs to figure out what should be the new state. But since our new state is simply bump the clock to the next one, we're not doing any computation there, but we are computing what the outputs should be. And the outputs in our state machine here happen to be those 12 control signals. So it's not unlike what we designed, it's just we have less or more of some of the things. Okay, anybody have most of those questions answered? Okay, well, we're going to move ahead anyway. We've pushed clear, we've released it, and we've been running this thing today. We know that the program counter is always set to zeros. Jumping ahead, we know that we're going to be entering T1. So the control signals that are prepared to be presented are going to be enable program counter. So I'll circle that for now. Which also means that because this guy is able to write just because of the enable, the bus is going to have 4 Z's and 4 zeros on it. So the 4 Z's and 4 zeros. Now, inside the MAR, since nothing has been put there, but we also didn't clear it, the value that's in here is the last address that's one after the halt instruction that halted the last program we ran. So there'll be an address in here. We don't know what it is, but if we were asked in words what it is, what has to be here, if we've run the machine before, which was part of the thing I said, it's going to point one past the last halt we encountered. Now, since we reprogrammed it, there might not be a halt there anymore, but this is an unpredictable number, which because we reran it, means we can't even hope to figure out what's in this. So this is 8 unknowns here. It happens to be what's ever at this address, but we don't know the address, so we can't predict what those values are. But they don't get cleared or anything. The instruction register contains 4 zeros and it contains whatever was on the right-hand side of the last halt instruction we executed, which is probably 4 ones. Now we know up here the first instruction is going to take this 0 and put it into the thing, so we know that load memory address register is also asserted in the control signals. So the 2 we have down there are, the second 2 in the list. And they're asserted, if they got a bar over them, they're asserted by being a 0. If they don't have the bar, they're asserted by being a 1. Everything else is non-asserted. Down the other side, we haven't a clue what's in here. We haven't a clue what's in here. We do know, however, that if we did know what it was, this is the sum of something we don't know, which is something else we don't know. But whatever's there and whatever's here is getting added up, and it didn't get cleared because of the clear. What's in the output register? Well, it's whatever we put there last, but we don't know what it is. We do know that the binary display exactly reflects this, so no matter what this is, they'll be turned on to match whatever's in the output register. So just like this is doing a known addition against, if we knew those numbers, we'd know the answer. Same thing down here. If we look at the binary display, we do know what's in the output register. We just don't know what it is without looking. And it would have been the last thing we did in output if the last program had an output. If it didn't have an output, this originally, when we powered it on, had random values in it. Anybody have any questions about that little exercise? How many people got a lot of those right? Scott, what sort of things did you miss?
I was thinking too hard about there being valid values in a lot of these when the right answer is we don't know.
Okay. That's a perfectly good thing to do, because until I show you that, you don't necessarily expect that. Anybody else want to contribute with something you were thinking? Remember, it's key to remember that there's only those 4 things that are changed. As a result of that, we may see other things. And because we're getting ready to start the program, we did know what this is going to put in the bus. We know about those Z's, for example. But let's look now at some of the wiring circuitry. That's this guy. Let's start down at the bottom with the power supply. We have a transformer, which is basically 2 coils with some metal stuck between them, and it uses inductance, which is kind of the evil twin of capacitance, but stores its data in a magnetic field, or stores its values, its electrons in a magnetic field, as opposed to storing not even electrons, so it stores its charge in the magnetic field, as opposed to on those 2 plates in a capacitor. But what happens is we plug this in the wall. We get 110, 115, 120, whatever the voltage in our house is. We fuse it so that if we're pulling too much current, the fuse blows and we don't shock ourselves. And then this takes, and it's a dropping thing, it's going to drop it down to in the vicinity of 9 volts. We're then going to pass it. Remember, this is alternating current, so it's going to look like a sine wave. It's going to alternately send data that way, that way, that way, that way. At 60 cycles a second. And when it gets there, it's going to be pushed through this diode from low to high to ground, or it's going to go from high to low to the signal. And what we're basically going to do is this is going to work like what we call a rectifier. The signal that came in that looked like a sine wave, when it gets on this side, is going to look like a bunch of humps. All of them, the up and downs, are all going to happen in the same direction. Put a big fat capacitor here to act as an integrator or a high-pass filter. I'm sorry, low-pass filter. I'm looking at the picture wrong. And it'll basically smooth this out. So yes, it has humps in it, but they're much smaller. We'll run that into this thing, which is a voltage regulator. The voltage regulator is hooked to ground, takes about 9 to 12 volts in, and produces the same signal but at 5 volts with a tiny bit of ripple in it that we remove with this other low-pass filter here. So we get virtually a steady 5-volt signal, which we can now treat as 5 volts DC. That's going to power all the chips in our system. Now we have some circuitry. Let's start with the simple stuff at the top. We have a switch. Notice this is just simply an RS latch. It has one position called start, the other called clear. If we set clear, this becomes not clear, and we know where these signals go. So pushing this to clear causes those 4 things we need it to do to happen. Releasing it causes the processor to start running our program at address 0 at low clock for T1. Now our clock comes from down here. We have 5 volts in. We have a 555 timer hooked up to work like an astable multivibrator. 38, or is that 38 or 36? I can't see it well enough. 18, let me actually blow that up a second. 36K, 18K. And it's going to be generating us a square wave. Why doesn't somebody go find a 555 calculator and calculate the frequency this is working at? 0.01 microfarad. RA is 36K. RB is 18K. Somebody go do that. Give me a green circle to tell me you're doing that. You can surely find a 555 calculator online. But some of you found it for the exam. A couple people did. They shouldn't have been using it, but they did. Shame on them. Anybody looking it up? I don't see any green circles. I don't want to go do it. You doing it, Scott?
I can do it.
Yeah, why don't you do it? Why don't you do it, Robert? Why don't you do it? Some of the other people. I mean, once you know how to do the calculations and you can pass a test on it, then we can loosen things up a little bit and you can use tools. But you need to know how to use the tool. You need the data sheet to figure out what these numbers mean. But now that we know, it's okay to let's check our answer. In this case, let's compute. What is the value of the clock we're going to see right here and what its duty cycle? By the way, if you actually sit down and build this computer, it works. So this literally in classes, and I'm talking 15, 20 years ago when these parts were much more accessible. My class would, as part of the semester, would build this as a project. And we would actually get this to work every year. And they'd write code that would work in an EEPROM and things. And it was a good experience for them. We're going to use the AT Mega to kind of do our practicing of programming. But from the good old days, this is actually one of the best computers you can use as an example of how to make one of these work. Anybody have an answer yet? Masu, what'd you get?
I got 2000 hertz.
So you got 2K hertz, right?
Yes.
What was the duty cycle?
For that, I don't know where to look. Duty cycle.
Okay, well, it should be one of the answers to the problem. Scott, do you have that? Can't hear you.
0.25.
Okay, 0.25 is, so it's a quarter on, quarter off. It's going to be off more than it's on. So it's 3/4 on, 1/4 off. This sort of thing. Is that what we're saying? Remember, the on time has to be longer than the off time because we charge through both, we discharge through one.
I gotta recheck my work. Yeah, I had it backwards. It's 0.75.
Okay, that's fine. Now, this is going to go into this flip-flop here. Notice this is a JK, so we know it's going to happen. It's basically going to flip this signal over, which is good for us because not only does it flip the signal over, but it squares it up. So it has a 50% duty cycle coming out here. So when we get over here, we have a low and a high at half the frequency. So instead of 2K, this is a 50% duty cycle at 1K, which is exactly what we need. So that means every T state is going to be represented by a click of this clock that's running 1,000 times a second. So how long is a T state? I'm going to get my grocery store calculator out of my thing here. So you all don't think I really have one and use it, but if we were meeting in person, you get to meet it. So if we have 1,000 hertz, how do I figure out how long that takes per cycle? We have 1,000 of these things a second. How do I know how long one of these is? Scott?
We just invert the number 1 over x.
So that's how long one T state takes. It's going to take us 0.001, which we would call what? What would be the name, the way we would describe this? Our rule was make 2 significant digits, so we need a 1 and a 0. We now shift this over till we get at least one of the significant digits. So it's going to be 1.0 milliseconds. On a test, that would be the right answer. So how long does an instruction take to execute? All of them except for halt. Robert?
Between 5 and 6 milliseconds. Well,
nope.
All the way it would be 6 milliseconds.
6 milliseconds. Should be a lowercase s there, by the way. So we could use this to compute how long a program would run, or various other things. How long does the halt instruction take to execute? Scott, what do you think?
That one's 3 milliseconds.
Well, we have to be a little careful with this one. That's a good answer, but think about this a second.
2.5.
We're doing all of T1, all of T2, half of T3. So how much is that? That's 2.5 milliseconds. because it stops halfway through T3. Okay, let's take our newfound knowledge here and move ahead. Notice that the clock can be controlled and gated by halt. So if halt goes low, this clock stops ticking. This is still ticking, but this guy stops and doesn't pass the clock, meaning we're never going to see another clock because the clock comes out of Q3, or Q here. Now this takes us into effectively an AND gate, which in the real machine has some interesting features. One of the things is, and we're not going to go through all the latching here. I will point out that halt also stops traffic through this gate. But we have the ability to put it in manual mode or leave it in automatic. When it's on automatic, the clock we get is this clock. When it's in manual mode, the clock we get is from moving this switch up and down. So when we start a program, we need to make sure we've moved this switch to low when we start the program before we release clear. And either the clock or this clock will pass through some clock buffers used to build up the number of things we're tied to, and also to add a little additional delay to clock so it and not clock are a little better synchronized. That pretty much introduces what's inside the SAP1 computer's control circuits. Anybody have any questions about that? Robert, do you have a question? There's your hand just up there.
No, I actually have a question. So
okay.
That
you remind me of the guy on a subway that walks with his hand holding onto the rail the whole time. Okay.
I assure you, I'm not physically holding up my hand this whole time. Okay. The manual switch, to me, that seems a lot like a debug mode.
It is. If you wanted to go step by step and look at what your program is doing, you would first of all put it into clear mode. You'd come here, you'd put single step into low, then you'd switch it from automatic to manual. Now, since you're in clear, it's holding the T1 at low, it's holding the clock at low, and it's ready. Well, it's not holding the clock at low because you are the clock, but it's holding the program counter, zeros, and it's put zeros in the instruction register. So what you do now is you say, okay, single step, go high, go low. It'll have done T1. High, low, T2, high, low. And then you can observe the circuitry with meters and things like that to see that it's really doing what it's supposed to do. So yes, it's absolutely a good, that's your Eclipse of this world. You know, it's your IDE. Okay. Let me see, what else, was there anything else on this page we needed to see? I think we saw the buffers. I wouldn't worry too much about those. They were to get the timing right on the real device, but not to worry here. Okay, now there's one other little detail thing that I want you to think about. Let's assume for a second that the accumulator, let's put it in two sets here, contains the number 1. And let's actually put them on the same line. I'm going to put that back to where it was. And the B register contains the number 2. What does the unit have in it right now? Robert, what do you think?
It would have 3.
Yeah. Okay, so just to make a note out of things here, this is the accumulator. This is the B, oh, not the V register. This is the B register. And this is the unit. we're doing an add instruction. So the next step we're going to be performing is we just moved it into the B register. The next thing we want to do is we want to take the unit and move it into the accumulator. Right, that's T6 of a thing. So let's pretend for a second, let me move some of this over, that this is on the low clock. Actually, let me even make another clock line in there. This is the low clock. This is the high clock. Here's the low clock. And there's the high clock. Where this is T5 and this is T6. Okay, so I actually put this into here sometime earlier than that. Okay. So it's still there. B, however, didn't get loaded until right here, halfway through T5. At this point here, I didn't know what was in B. It means I also don't know what's coming out of the unit. I know it's the sum of 1 and something, I just don't know what it is. Now we enter T6. In T6, the answer goes on the bus, and the others keep the same value in them that they had. So this value goes on the bus. So let's actually write the bus over here as well. But way back here, bus was whatever we were getting ready to load into the B register. Well, right, that's what we ultimately wrote, and it's held for the entire T state, so it was still here. Which means this guy is still there. We'll get to him in a second. Now, when the clock rises, what's in the unit is going to get put into the accumulator. The same thing is still in the B register. But now the unit is adding up 3 plus 2. 3 plus 2 is equal to 5. It has a wrong value in it for the answer, which also propagates to the bus. Because we're never going to see in this T state another low to high transition, even though the accumulator is reading from the bus, it managed to snag this off the bus right before the problem got worked and put this on the bus. So during T5 and T6, we got to be very careful about looking at what values are changing, because remember, this guy's always adding whatever A and B are. And if he happens to, like in here, say enable the unit, his value will also be on the bus, being very careful that we grab A off the bus before it changes. So that's a little subtle thing that goes on. Now, this is even worse for subtraction, because don't forget that during the last part of the T state, we're going to change B to be its 2's complement. We're going to work a subtraction problem here, so the value of U will change, meaning the correct answer will go on the bus here. We're going to snag the correct answer into A, which means this will change, because now we're doing a subtraction problem of the correct A against the, or correct B against the wrong A. Meaning what's on the bus will be totally wrong, only to be compounded when we go to T1 of the next state. Because in T1 of the next state, the unit no longer will be holding the subtraction problem. It will be holding the result of the addition problem of us plus the correct answer. So you want to think through those two kind of as a not to be turned in, but I might ask for it anyway. You might have to write it down type of thing in some form on Monday's class. You need to review very carefully this machine. You need to be able to quote numbers, facts, and figures about this just pretty much without having to go to your notes. You won't get done in time if you do. There's a reasonably moderate chance, I like that type of a phrase, that we will do something called a quest. A quest is only known in the SAP 1 world. It's kind of a hybrid. It's not a test. It's not a quiz. Therefore, no accommodations apply. It is, however, something for which you might be asked a bunch of questions. Some of the questions I ask you tonight would be fair game, or questions about what we just talked about up here. You might want to go through those very carefully and think about what's in the registers, what's on the bus at every moment in time, so you don't get caught up and trapped by making some assumptions as opposed to doing what the machine is doing and literally making it do what you told it to do. So I would study up on the SAP 1 and become kind of an expert on it before Monday's class. Really a low chance I'm going to give a quest because I have a test in my other class next week, as well as we have a lot of stuff to get through next week in this class. Anybody have any questions that I can answer right now? I would strongly suggest working with others on this study. You know, have a study session or something with some other people rather than just trying to wing it on your own. Because all you need is one wrong assumption and, you know, on these computers, because the one thing a computer does is it does everything very precisely, but it does it exactly as you told it to do it. And so if you make assumptions about how it's going, like programming languages help you out. Assembly language doesn't help you at all. It does everything exactly as you told it to do. And if you are making assumptions like it works this way, but it doesn't, you'll be bit because it's going to do things that you're not expecting and you'll get wrong answers. And since most of the rest of the semester is going to be focusing on these various machines and their assembly languages, you're going to want to make sure you get on board right now, because literally we've talked about the architecture of everything you would run into if you were designing yourself a machine today. There are other things and think of them as modules that you could add to it to make it faster or more optimized or have less errors, but they'll all be done in terms of things we've already seen. Okay, I think we've used up enough of the evening. Any final questions before we go? I will attempt to get the test mostly graded over the weekend. If you receive an email now or next week about turn in the work, all that means to do is go back to what you did when you took the quest, find that one question, cut and paste it either as an attachment or part of your email if it's short, and send it to me so I can make sure that you were doing your problem the correct way. And if you don't get something, don't worry about it. Dante, you have a question?
Yeah, I was just wondering, if we like wrote it out on a piece of paper, do you want us to just transcribe that into the email? Or do you want us to like get a screen grab of it?
Whichever would work for you the best.
Okay.
Any other questions? Okay, well, you guys now are the SAP 1 King. Make yourself a little paper hat, walk around your house, and everybody you see, tell them you're the expert now and make them bow to you or something. Because you guys really, you now know this, one of the big secrets of microcontrollers, which is once you understand this, yes, they're complicated, but when you can grasp this in your head, you really do understand microcontrollers and microprocessors. Okay, good night. I will see you all, I guess some of you tomorrow. Is tomorrow Thursday? Yeah, I guess it is. And I will see the rest of you on Monday night.
夜明けか。あら、ルーデ朝稽古精が出るわね。なんだ、フェリシアか。早いな。ええ、お兄様の朝食のお支度を。